Welcome to the deep dive. Here we try to take fascinating, often complex information and really boil it down to the key insights just for you.
Yeah, we know you're curious, you want to understand these big ideas, but, without getting totally overwhelmed, you're looking for those aha moments.
Exactly. And today we're diving into something pretty cutting edge, neural Turing machines. NTMs for short.
hmm We're looking at a really interesting research paper from Google DeepMind.
Mhm.
It introduces this kind of new way of thinking about neural networks and memory.
Right. So, okay, at its heart, what is an NTM? Let's break it down.
Well, imagine a standard neural network, the kind that recognizes faces or translates languages.
Okay, got that.
Now, give it something extra, like an external memory bank it can use.
Like giving a computer RAM alongside its processor, something like that?
That's a great way to think about it. The NTM controller, the network part, can interact with this separate memory using something called attention.
Attention, okay.
Yeah, and the researchers, they even connect it back to theoretical ideas like the Turing machine, with its infinite tape, or just standard computer architecture. Processor, memory, distinct parts.
But there's a twist, right? What makes the NTM really stand out?
The really key thing is that the whole setup, the controller, the memory interaction is end-to-end differentiable.
Okay, differentiable. Let's unpack that a bit. Why is that so important, especially for training these things?
Right. So think of it like this. Differentiability lets us see exactly how tiny changes in the network affect the final output, especially the errors.
Uh-huh.
This means we can use standard methods like gradient descent to automatically tune the network, to adjust its connections, and, crucially, how it learns to use that memory.
Wow. Okay, so it's not just giving it memory, it's that the network learns the best way to use that memory all by itself during training.
Precisely. It learns the read and write operations. That's the fundamental shift.
Okay. So our mission for this deep dive, figure out how NTMs work, why DeepMind developed them, and what these first results hinted at for the future of AI. Sound good?
Absolutely.
Let's dive in.
Where should we start? Maybe the motivation? Why do they feel the need for this?
Good place to start. So the paper points out that, machine learning is great at finding patterns in complex data, image recognition, speech, amazing stuff.
Yeah.
But it's generally overlooked a couple of things that are absolutely fundamental to how we traditionally write computer programs.
Which are?
Explicit control over the sequence of operations, step-by-step logic, and using external memory to store and retrieve information deliberately.
Right, that makes sense. Programs run instructions, they use variables stored somewhere. How did neural nets usually handle that kind of thing before NTMs?
Well, we have recurrent neural networks, RNNs. They're quite powerful for sequential data like text or time series.
Because they have that internal memory. Right, they
Yeah.
remember past information in the sequence. Exactly. They have an internal state that carries context along.
Right.
And theoretically, they're actually Turing complete. Given enough resources, they could compute anything.
Ah, but there's the catch. Theoretically, the paper suggests it's not so easy in practice.
Right. Just because an RNN can do something in theory doesn't mean you can actually train it to do it reliably or efficiently, especially for complex algorithms. It gets very difficult.
So the NTM is proposed as a kind of enhancement.
Yeah, an enrichment, as the
Yeah.
paper calls it. You take a standard network, maybe an RNN, and you give it this large external memory it can specifically address. A bit like how a Turing machine adds that memory tape to a simpler finite state machine.
But the crucial difference, again, is the learning part.
Yes. Unlike a fixed Turing machine, the NTM learns how to use the memory through gradient descent because the whole thing is differentiable. It learns the program, in a sense.
This really does remind me of how humans operate. We have our general smarts, but we rely so much on working memory, right? Holding things in mind for a task.
They make that exact parallel in the paper. Human cognition heavily relies on this temporary storage working memory where we hold information and apply rules to it. Quick manipulations.
So the NTM is kind of mimicking that, handling temporary information and applying learned rules.
Kind of, yeah. Applying approximate rules to rapidly created variables, as they put it. And like our attention shifts, the NTM uses its attention mechanism to focus on parts of its external memory.
But how does it differ from, say, scientific models of working memory?
While many cognitive models of working memory often assume fixed procedures for handling symbols or information, the NTM's big advantage is it learns how to use its memory. It's not programmed with fixed rules. It finds them.
That's a really key distinction. Okay, so the paper also connects this to wider research psychology, neuroscience, even linguistics. How does the NTM fit into those pictures?
Let's touch on psychology and neuroscience first. Working memory is huge there. You have ideas like the central executive directing attention, memory buffers.
And capacity limits, like Miller's famous magic number 7.
Right, though the researchers kind of cheekily mention they want to go beyond those limits. Neuroscience points to brain areas like the prefrontal cortex and basal ganglia being involved. There are computational models trying to simulate this too.
The paper mentions one by Hazy and colleagues. What's the link?
Yeah, the hazy model is interesting. It had mechanisms, a bit like LSTM gates, to control information flow into memory slots. But critically, it didn't really have the sophisticated addressing mechanism the NTM has for pinpointing specific memory locations.
And why is that specific addressing so important?
Well, researchers like Gallistel, King, and Marcus have argued that something like precise addressing might be crucial for how the brain handles structured information flexibly.
Okay. And what about the cognitive science and linguistics angle? There were some big debates about connectionism, right? Neural nets versus symbols.
Oh, absolutely. Back in the 80s, Fodor and Polishin raised big questions about whether neural networks could handle things like variable binding.
Variable binding, like knowing the dog is the subject and the ball is the object and the dog chased the ball. Assigning roles.
Exactly that. And also processing structures of varying lengths, like sentences. Traditional networks struggled with that dynamic role assignment and variable sizes.
But people have worked on that since within the connectionist approach.
Yes, definitely. Hinton, Smolinski, Turetsky, Plate, Kanerva, they all explored ways to tackle these issues. The NTM, with its external memory and learned addressing, is seen as building on and potentiating those earlier efforts. It's a step toward handling these variable structures, which are such a hallmark of human thought.
Right. Okay, let's swing back to AI itself. RNNs were mentioned as a stepping stone. We know they handle sequences.
Yes, their dynamic internal state lets them process sequences where context matters. Think speech recognition, text generation, machine translation, all involve variable length inputs or outputs.
And LSTM long short-term memory was a specific type of RNN that was a big deal.
Huge deal. LSTMs largely solve the vanishing and exploding gradient problem. This meant they could learn dependencies over much longer timescales than simple RNNs. They use these clever gates to control information flow, letting them hold on to relevant stuff for longer. A better short-term memory, essentially.
So LSTM improved the internal memory, but NTM goes for external memory. Were there other related AI ideas that influenced NTMs?
The paper mentions two key things: differentiable attention mechanisms, ways for networks to learn where to focus and work on learning sequences of actions, like program execution, often using RNNs. Both are clearly related to the NTM's ability to learn focused read-write operations on memory.
Okay, that covers the motivation and the background nicely. Let's get into the architecture. What does an NTM actually look like under the hood?
Right, so fundamentally two main pieces. You've got a neural network controller, could be feed-forward, could be recurrent, like an LSTM, and then you have the memory bank.
And the memory bank is just like a big grid of numbers.
Pretty much. An N by M matrix. N locations, and each location holds a vector of M numbers. So N rows, M columns.
And the controller network, that's the brain. It takes input, produces output, and talks to this memory matrix.
Exactly. It interacts with the memory using heads. Think of these heads as outputs of the controller specifically designed to manage the reading and writing.
And this is where the differentiability comes in again. Even though the memory stores discrete values, how does that work?
Through blurriness. Instead of picking just one memory location, like a computer's address bus, the NTM heads interact with all memory locations to varying degrees.
Varying degrees, like a weighted interaction.
Precisely. Each head outputs a set of positive numbers that sum to 1 over all the memory locations. This weighting says how much that head should pay attention to or interact with each location. You can be sharply focused on one spot or spread out.
So it's a soft focus, not a hard selection.
Okay, let's dig into reading and writing. How does it use these weightings to get data in and out? Reading is fairly straightforward. A read head generates its weighting. The value it reads out is simply a weighted average of all the vectors currently stored in memory. Locations with a higher weight contribute more to the final read vector.
Okay, so it reads a blend of the memory content guided by the attention weighting. What about writing? You mentioned it's inspired by LSTM gates.
Yes, writing is a two-step process. Erase, then add. First, the write head outputs its weighting, but also an erase vector. This vector has values between 0 and 1. For each memory location, you multiply its current vector by one weighting erase vector. Effectively, if a location has a high weight, and the corresponding erase vector element is close to 1, that part of the memory vector gets pushed towards 0. It's selective forgetting.
Targeted erasure based on the weighting and this erase vector. Got it. What's the second step?
The add step. The write head also outputs an add vector. This vector is then added to the memory, but again, the amount added to each location is scaled by that same attention weighting used in the erase step.
So you erase parts, then you add parts, both guided by the same focus.
Exactly. And because of how math works, the order of erasing and adding, even across multiple heads writing at once, doesn't change the final outcome. It's commutative. Plus, these erase and add vectors give really fine-grained control over modifying the memory content.
Okay, that makes sense. Now, the paper really highlights the addressing mechanisms. This seems key to the NTM's power. What are they?
This is where it gets really clever. There are two complementary ways the heads can generate those attention weightings we just talked about: content-based addressing and location-based addressing.
Content-based. Does that mean finding memory based on what's in it?
Exactly. The controller produces a key vector. The system then compares this key to the vectors currently stored in every memory location, usually using cosine similarity, how much they point in the same direction.
Ah, so like a search query.
Precisely. Locations whose content is very similar to the key get a high weight. The controller also outputs a key strength parameter, beta, to make this similarity focus sharper or softer. Great for retrieving things when you know roughly what you're looking for.
Makes sense. What about location-based addressing? When is that useful?
That's designed more for things like stepping through memory sequentially, like processing items in a list or maybe jumping back to the start. Think iteration or random access based on position, not content.
How does it manage that? Shifting the focus somehow.
Yeah, fundamentally it works by applying a rotational shift to the weighting. If the focus is mostly on location 5, a shift of +1 would move the main focus to location 6, wrapping around if needed. A shift of -1 moves it to location 4.
Okay, two different ways to focus attention, but how does it choose? Or combine them? The paper seemed to suggest they work together.
They do through a sequence of steps, which is shown in their figure 2. It's quite ingenious. First, there's an interpolation gate, let's call it.
A gate, like in LSTMs?
Sort of. This gate is a value between 0 and 1. It blends the weighting, calculated by content addressing in the current time step, with the final weighting the head used in the previous time step.
So it can choose to either stick with where it was looking, location focus, or jump based on content, or somewhere in between.
Exactly. It interpolates between the content-based focus and the previous location-based focus. After this blending, the head produces a shift weighting.
What does that do?
This shift weighting defines how much to shift the focus. It's usually a small distribution over, say, shifting back 1 step, staying put, or shifting forward 1 step. This distribution is then used to perform that rotational shift on the interpolated weighting we just talked about. It's like a weighted average of shifts.
Okay, so it blends content and previous location, then it potentially shifts that blended focus.
Right. And one final touch. Because interpolation and shifting can sometimes make the focus a bit spread out or disperse over time, the head also outputs a sharpening factor, gamma.
To tighten the focus back up.
Yes, gamma, which is always 1 or greater, sharpens the final weighting distribution, making it more peaked and less blurry again.
Wow. So combining all that, it sounds like the NTM can operate in different modes. Just use content, then shift, or shift relative to where it was before.
Exactly right. It gives the controller a lot of flexibility in how it accesses and manipulates the memory.
Let's talk about the controller itself. The paper mentions they tried both recurrent, like LSTM, and feed-forward controllers. Pros and cons.
Yeah, they draw that CPU-RAM analogy again. The controller is the CPU, memory is RAM. A recurrent controller's internal state, its hidden activations, are like the CPU's registers.
Meaning it can hold information internally across time steps?
Yes, it can mix information easily over time, which is powerful for many tasks. A feed-forward controller doesn't have that built-in temporal state.
So what are the trade-offs then? Is feed-forward simpler?
It can be perhaps easier to analyze its behavior at a single time step, and it can sort of mimic recurrence by reading and writing to the same memory location repeatedly. But there's potential bottleneck,
Which is?
the number of read and write heads. If a feed-forward controller only has, say, 1 read head and 1 write head, it might be limited in the complexity of the operation it can do in one go. Like maybe it can only transform 1 piece of data at a time easily.
Whereas a recurrent controller could read something, hold it in its internal state, read something else, and then combine them before writing, even with fewer heads.
That's the idea. The internal state gives it more working space, potentially overcoming limitations imposed by the number of heads accessing the external memory.
Okay, architecture and mechanisms covered. Now for the really exciting part, the results. Did it actually work? They tested it on some simple algorithmic tasks, right?
They did. 5 tasks to start: copy, repeat copy, associative recall, dynamic engrams, and priority sort. Simple, yes, but designed to test core algorithmic capabilities.
And the key goal wasn't just solving them, but generalization, right? Could they perform beyond the specific example seen during training?
Exactly. Could the NTM learn a compact internal program that worked on, say, longer sequences than it was trained on? That's the real test. They compared NTMs with both feed-forward and LSTM controllers against a standard LSTM baseline.
Okay, let's go through them. The copy task, store, and recall a sequence. What were the findings there?
Pretty dramatic, actually. The NTMs learned much, much faster than the standard LSTM. Their error rates dropped significantly lower. Figure 3 in the paper shows this really clearly.
Okay, faster learning. What about generalization, longer sequences?
That was even more impressive. The NTMs generalized remarkably well to sequences far longer than the training examples. You can see this in Figure 4. The standard LSTM, however, completely fell apart once the sequence length went beyond what it had seen in training. Figure 5 shows its errors shooting up.
Wow. So the NTM really seemed to learn the algorithm of copying, not just memorize patterns. Did they
Mhm.
figure out how it was using the memory?
They analyzed the head movements and hypothesized a pretty sensible algorithm. Essentially, find the start of the memory, write the input sequence location by location, then jump back to the start and read it out location by location.
How did it manage the jumps and sequential movement?
It looked like a combination using content-based addressing, maybe finding a special star 10 marker to jump back to the beginning, and then using the location-based shifting mechanism to move step by step through memory for writing and reading.
And they needed those specific mechanisms, like the relative shifts and the sharpening.
They argue those were crucial for the generalization. The visualizations, like in Figure 6, are quite compelling. You see these sharp focus points moving smoothly across memory, with reads and writes aligning perfectly.
Okay, that's a strong start. What about repeat copy? Copying a sequence a specific number of times.
Right. For this one, both NTM and LSTM actually managed to learn the task pretty well within the training range. Figure 7 shows that.
Ah, but the generalization test again.
That's where the difference showed up. NTM generalized better to longer sequences, although it sometimes struggled a bit with getting the exact number of repetitions right, or placing the final end of sequence marker correctly when the repeat count was outside the training distribution. LSTM, though, failed to generalize on both sequence length and repeat count. Figure 8 shows that gap.
So the NTM learned a kind of basic loop.
Seems like it. They suggest in Figure 9 it learned a simple extension of the copy algorithm. Just repeat the sequential readout phase multiple times.
Interesting. Next up, associative recall. Learning pairs and recalling one item given the other.
Here again, NTM learned significantly faster than LSTM.
Yeah.
Interestingly, the feed-forward NTM was the fastest learner on this one, Figure 10.
And generalization to more pairs.
Much, much better with the NTMs, Figure 11. The strategy it seemed to learn was quite clever too, based on Figure 12.
What was the strategy?
It looked like it learned to store some kind of compressed representation of each item pair in memory. Then, when given a query item, it would compress that, use content addressing to find the location storing the query item's representation,
Okay.
and then use a location-based shift, probably just a shift of +1, to read out the associated item stored right next to it.
That is clever. Using content to find the spot, then location to get the related piece. Okay, dynamic engrams. Predicting bits based on changing statistics.
This one was about adapting quickly. NTM did perform better than LSTM, a small but significant edge, but neither quite matched the theoretical optimal performance of a perfect Bayesian estimator, Equation 10, Figure 13.
How did the NTM seem to achieve its advantage?
The analysis, like in Figure 15, suggests it was using its memory as a kind of counter. It was keeping track of how many ones and zeros followed different 5-bit histories, effectively building a statistical model on the fly in its memory to make predictions.
Using the memory like a dynamic lookup table for probabilities. Makes sense. And the final task. Priority sort. Sorting vectors based on priority numbers. That sounds hard.
It is definitely more complex algorithmically.
Yeah.
And yes, the NTM substantially outperformed the LSTM here, Figure 18.
How did it seem to approach sorting?
Based on the memory access patterns, Figure 17, the hypothesis is that it used the priority number associated with each input vector to calculate where in memory to write that vector. Higher priority maybe goes near the start, lower priority near the end, something like that.
So it writes them into the correct sorted position.
Sort of, yes.
Yeah.
Relative positioning based on priority. Then, to output the sorted sequence, it just reads sequentially through the memory from start to finish.
That's a neat way to implement sorting. Any other interesting observations on that task?
One thing they noted was that the feed-forward NTM needed more read-write heads to get its best performance on sorting. This might hint that sorting is intrinsically harder to do well without either recurrence or significant parallelism in memory access.
Okay, so let's wrap up these results. What's the big picture takeaway?
I think the big picture is that NTMs clearly showed they could learn simple but actual algorithms directly from examples. They learned to copy, to loop, repeat copy, to do associative lookup, even to sort and build statistical models.
And crucially, they generalize these learned procedures way beyond the training data, especially compared to a standard LSTM.
Exactly. They leveraged that external addressable memory in ways the LSTM just couldn't. It really points towards neural nets being able to learn more program-like procedural behaviors.
Yeah, it's really fascinating. These connections back to biological working memory seem less like analogy and more like maybe a shared principle.
It certainly pushes in that direction. The idea that differentiable memory and attention mechanisms are powerful tools for more complex computation seems really validated by this work.
It feels like a significant step forward for machine learning.
Absolutely. A new building block, potentially.
So, as we finish this deep dive, here's something for you, our listener, to think about. Consider the implications here. We're talking about machines that don't just recognize patterns, but can potentially learn to execute algorithms, learn procedures in this flexible, data-driven way.
How could that change AI? What new applications become possible if systems can learn algorithmic tasks rather than needing them explicitly programmed?
And what new challenges might pop up? As we build even more complex networks with more sophisticated memory, what are the hurdles? What are the risks?
Really good questions to ponder. If this sparked your interest, definitely check out the original DeepMind paper. There's a lot more detail in there.
Well, thanks for joining us on this exploration of neural Turing machines. Until next time, keep thinking deeply.